Everybody see my screen? Cool. Thanks everyone for sticking around. So my name is Chaima and I'm a PhD student at Northeastern University. And today I will be presenting MAT's a mixed methods approach for the analysis of debugging sequences of beginner programmers. So the idea behind this work is how we can try to combine qualitative analyses and quantitative analyses to kind of make our observation more scalable, to look at patterns of debugging, but also try to identify unique paths. And so how also those sequences, how much information they give us compared to aggregate data. And so for this study, we are using Maze Journey, which thankfully Mia presented earlier on, but if you want more information about the game, I would be happy to talk about it afterwards. So for the study, we used the 10 first levels of the game, and it has like simple instructions, so move and rotate commands, sequence logic, and simplified for loops. For our study, we had middle school students, 6th, 7th, and 8th grade, and they were first introduced to the game during class by either a researcher or the teacher. And they played during class, and they were able to log in and play more at home if they wanted to. And we had 885 different profiles. I call them profiles because a student could have more than one. They could create more profiles if they wanted to. And we had 9,452 code submissions to analyze. And so the idea behind the approach is to look at how students went from a wrong code submission to a correct one in each level. And to do so, we first start by looking at our data and try to identify the types of errors that are there. And then we label automatically each code submission according to the errors that are in that submission. And we code all the different errors, not just the one that they got an error message for. And then we represent the sequences as a state and action representation, where a state is the number of errors for each type, and the action is an abstracted version of the change that they made to their code. And finally, we look at their sequences in a visualized graph, and then we try to look for patterns and uniqueness there. So for the types of errors, first we have the puzzle errors, where the code runs, but it doesn't solve the puzzle or solve the problem. Then we have structure errors, where players, for example, have code outside of the main function or have commands that are not applied to objects. And so it's like mostly about the structure. And then we have reasoning errors, which include misrepresentation and intrusion. And these are like very borrowed from Katz and Anderson error classification. And so here these are errors where they would use a variable that existed in a previous level, but not in this level, or exists in the example, but not actually in the level they're trying to solve, or they used code that would work in another programming language, but not in this one. And finally, we have also syntax errors, so like missing semicolons and curly brackets and upper lower case. And finally, undefined errors are errors that we could not categorize automatically. So this is how it would look like for a code submission. We find the label errors, so like wrong argument and object does not exist, and then we will just label them as syntax, reasoning, and so on. And so for each code submission, we would have a final state representation as numbers for each of the error types. And for the action representation, we have whether they added, removed, or changed code, how big was that change relative to their previous code, and if that change if that change is an addition or a change, then if it was existing in their previous code, so if they were using some of the same things that they used before. And so this is how the whole representation would look like, from a wrong code submission to a correct one, or sometimes a wrong code submission to quitting. And what we could see is, like, for example, we were also expecting to see more of clusters, but what we could see is basically high-performing students doing kind of the same thing, and then everyone else doing various stuff. And so high-performing student would go through very linearly, would have mostly one error at a time and do very small or medium code changes and reuse code that they've used before. As opposed to struggling players, we could see them like their sequences is farther away from the performing sequence, and we can see their sequence characterized by loops, and so they will be stuck in the same state for a long time, or even if they get out of that state, they will come back to the same state with similar types of errors before. Comparing, for example, students with the relatively same amount of errors, for example, for B and C, we see that, for example, if it was with aggregate data, we will think of them as the same, like struggling students. But in fact, if we look more closely, we see that, for example, player B had a lot of like changes that went more like less systematic at the beginning, but more systematic as they went through the debugging process and tried to fix one error at a time and made medium to small code changes, as opposed to player C was doing a lot of large code changes and a lot of also running their code without any change, which can probably mean like they were frustrated and just hitting the run button without like knowing what's really going on. I think so. I was trying to go very fast.
And you're at about 6.5 minutes. So.
Okay, sorry. So yeah, we had like the biggest limitation is that we have a small number level. Things are not very complicated, so less opportunities for interesting errors to happen there. Yeah, and only clusters for high performing students. And also, like as we abstract our data, we lose a lot of the information. So it's a lot of like trade-off whether how much we want to abstract versus how much information we want to keep to have meaningful information. And yeah, thank you everyone, and sorry for keeping you here.
No, it's okay. It's a lot. I think this is wonderful. Thank you so much, firstly. I didn't do as good a job timekeeping either because the questions were so good, and this is our first meeting, so it's on me. So questions. I wrote in the chat that I thought it was an interesting coding scheme to look at the size of the code change relative to the original code. I thought that was a really interesting way. I wonder how you came about choosing that.
Yeah, it was because like there was a lot of variety for the levels on how much code they have to write. So a big code change would be very different if they had to write one line of code versus if they had to write 6 or 7 lines of code. So it made more sense to make it how much in between each code submission, how much change they do relative to the previous one.
Great, well, thank you.